if someone mentions the degrees with some funny language like degrees, minutes, and seconds. So that's what I'll tell you how to describe an angle with degrees, minutes, and seconds. You're working on your identities. You're working on remembering, memorizing whatever you need to do to study those identities on our formula sheet. And I thought I would share some quick way of remembering the Pythagorean identities. Okay, so let's get started. I'm going to take a tour for a second of the website just to show you some stuff that's happening. And I'm opening that up, and we're looking at our website right now. And we're looking at our week 3 page. So the week 3 page, I gave you a link to the tutoring center if you're interested in any of the tutoring services they have available for you. But this week we're going to look at sections 2.1, 2.2, and 2.3. I'm going to open up chapter 2. Remember, if you click on any of our weeks, like let's look at week 2, under video, you have links to all the class sessions, any recommended problems I've done on video, or the playlists where I collect all the class session videos, all the recommended problem videos, all the topics. So that might be helpful. Say, here's all the recommended problems people have asked that I've made videos for so far. And not a lot, but you're just getting started. And then if you want to see all my Math 121 stuff, you could just click on the YouTube channel, Dave's Web Corner. Got Math 121 things, class session videos, recommended problems, topics, or other classes. So you can find those playlists every week in the video section. And you can also find a complete list of all the class sessions in the resources page here at the top. Back to homework, because you got some homeworks coming up due tomorrow. Remember, every week you see the homeworks that are due. I'm looking at the week 2 page. I'll look at the week 3 page in a second. Or the week 2 page gives you a preview of what's due tomorrow. You get the homework number 1, the written homework, and then you're supposed to have completed the first 5 sections in the XYZ homework. You can ask questions, inside the XYZ homework while you're working on it. And I've answered several questions there, and I keep up with the questions there too. I tend to be more helping and not answering in there because remember, the homework is completely the XYZ homework. That's what you're doing. And we can use book examples to show you how to do lots of things. But in the questions you ask inside the homework system, those will give you a hint or a prompt. And they link you to the book where you can see how to do those problems too. So homework number 1, that's due tomorrow. And that's that sheet of paper. Remember to submit that as a PDF file and to name it so that I can keep it straight, so that you can keep it straight. Under the syllabus, we describe how to do that. Here in the expectations, you can drop your assignments into the Dropbox right next to the homework, but just try to label your files. Last name, first name, homework number 1, Math 121, what section you're in. Now, I'm going to definitely help you out as you get used to that because, you know, some people are snapping me pictures or just giving me things with different names. I'll make some adjustments here, but the target is that you submit your homework as a PDF document and you name it this way, mostly because I get a lot of papers and I got to keep them straight and not lose anything. Here's another thing that happens too. You submit the paper, you give it the right name on the file and everything, but when I open up the file, your name is not written on the paper that you submitted. If an accident happened and I lost that file name. Very unlikely, but it could happen. Make sure you write your name on your paper, just like you were submitting an ordinary paper, okay? So keep track of stuff like that. Remember, if you want to easily create a PDF document just by snapping a picture with your phone, these two programs that I put in the syllabus under required materials, Apple Notes and Adobe Scan, you can use those two programs to just snap a picture of your phone, and your picture automatically gets converted to a PDF that you can share. And PDFs are really useful because they're easy for me to write on and return to you. And now we're headed towards the question that was asked: where are the grades? How do you get the homework back? Et cetera, et cetera. So let's go into week 3. And I just want to show you the homework that you're looking at in week 3. Now notice, homework due tomorrow, homework number 1. But also you have a homework due a week from tomorrow, and that's homework number 2. And that is now posted on the website. So here's a new homework problem to do, and I want you to find all the missing sides and angles of this triangle. Okay, so that's from the stuff that we did in the previous week. Excuse me. And now, again, for next Tuesday, new sections in the book 2.1, 2.2, and 2.3. Today, we'll talk about sections 2.1 and 2.2. Okay, where are the grades? First, I'll tell you where they are not. They are not in e-learning. And you recall from the first day and from the message I posted on e-learning, I'm not going to put anything in e-learning, not grades, not anything like that. I've seen too many accidents happen in that space. Second place, they're not in the XYZ homework, although the XYZ homework keeps track of the things you get right and wrong, and it'll show you your grade. But you've got things in there like the chapter reviews that are not part of your grade. You've got some of the extra sections that I leave turned on, even if we're not doing them, so that you can get some practice. So the XYZ homework just tracks everything that you're doing in there, but we're not using every section of the book, and we're not using the chapter reviews. Those are strictly in there, turned on, so you can practice with them if you want to. What I'm going to do for your homework, and you're going to see it a couple days after you give me this first homework, you submit the first homework, and then I'm going to, make notes on it, give it a score, and return it to you. And I'm going to create a folder that I can share with you in the Google Drive, and I will give the address of that folder to you. And in that folder, I will put all of the papers I return to you, any exam I return to you, and any grade report that I generate for you. Now, so far, you have no papers submitted or graded or exams, and so I haven't opened up that folder for you yet. I just want to get one thing at a time. First, we were getting into the computer homework, then we were getting into this written homework. And now in the next week, you'll start to see papers come back to you. And I'll tell you what your current grade is. I mean, we're very early, so it doesn't represent a grade, really. It just kind of tells you what your progress is. So I definitely think you want to keep track of your own grade, but I'll give you a grade report, and you can say, wait a minute, the XYZ homework says I got 23 points, not 20 points. And then I can, double check, because I can make mistakes when I'm counting things too. So first mission this week is for you to hand in these 2 homework ideas, the written homework that we're looking at, and finish sections 1.1 through 1.5 in the XYZ homework. Then into this week, beginning of next week, I'll give you the link to a folder where I will return your papers and your grade reports. And once you see that happen, then it'll make more sense. So I'm going to leave it at that right now. So maybe that helps. And right now we're talking to a few people right here. We've got 13 people hanging out. And among the trigonometry course I'm teaching, I think I have 38 people available. So I'm going to have to write this in an email for everyone later anyway. So that'll be coming at you near the end of this week. Okay, so far so good. I also want you, and if you have any more questions, just throw them into the chat or speak them out. I also want you to look at the handout section here in week 3, because I've just, expanded that and organized that a little bit for you. So these are all kinds of handouts that might be useful to you. And announcements that other people gave me, link to honors program, link to tutoring center, what the fundamental trig identities are. Now, this is a big one, of course. We have to know everything on the sheet, and then more formulas are coming at us later. Last week, if you were in class, I was panicking because I had this upper left diagram backwards. I had a Y where the X is, and I had an X where the Y was. That was absolutely terrible. And I didn't see it until I read it with you in class. So I've corrected this worksheet now. If you see any other errors on it, make sure you let me know. But these are some of the formulas that we're working on currently. You've defined the trigonometric functions. You know how to define which ones are reciprocals of which ones, those things you should know. You know the quotient identities. And we're going to go in a circle. First thing we're going to do today is I want to update you on the Pythagorean identities, how you can use them, because that fits one of the questions you asked. And then we'll talk about right triangle trigonometry. And that will make sense out of the co-functions. When I talk about right triangles, then you will see why people call it sine and cosine, secant and cosecant, tangent and cotangent, or you'll begin to see that. And then we can use the so-called co-function identities. Next week, we will make it all the way full circle, and we'll be talking about calculations, not just in degrees, but in radians. Even after this sheet, I've got another sheet to add to this, but one piece at a time. Let's focus on learning this sheet first. Okay, next step. Where are we going? So you see the homework due tomorrow. You see the homework due in 1 week from tomorrow. You see the handouts. You see the place where you can catch the video and some Desmos worksheets if you want to look at them. We'll use Desmos more later. This is the outline for this week. And I think basically we're going to be doing section 2.1 and 2.2 almost completely done with 2.2 today. That'll get you launched on that. Okay. Are there any other questions you want to check out before we do that? If so, you can just throw them in the chat or speak them out. As time goes on and you get used to the system, I won't always spend this time reviewing the website. This is what you need to start with every day when you work in the class. What's on the website? What's the homework? What's the handouts? What videos can I watch? What's the outline? Okay, let's get working on that. Okay, back to paper. And got this going on. I'm recording. By the way, I issued you calendar invitations for the rest of the semester. So if you want to put those on your calendars, that's a handy way to just click and join the class sessions. And I also did some learning over the weekend and figured out how to make the sessions automatically recorded so that I don't have to fuss about pressing the recording button. And now that came up in another class because there was another class I had last week where I forgot to press the recording button and did not have the session for them, which was not excellent. Okay, let's look at this picture here. Let's look at Pythagorean identities. Then we'll talk about right triangle trigonometry, trigonometric values of any angle, and describing angles more precisely with degrees, minutes, and seconds. Okay, remember that when someone gives you an angle, theta, in the plane, it could be in any quadrant. What they do is they specify an initial side on the positive horizontal axis. That's always the place we start. They specify a final side, a terminal side. This time I've put it in quadrant 2. And you can find the sine, cosine, tangent, cosecant, secant, cotangent. You can find all 6 trigonometric values just by picking a point on that terminal side, x, y. If we are in quadrant 2, then I know x will be a negative number and y will be a positive number. And I have to account for that. And the distance from the origin to xy, that's what I call r, radius or distance from the origin. R is always positive because I'm using it to measure that distance. But remember, x and y can be positive or negative. Remember the definition from your sheet. Sine is y over r, cosine is x over r, and tangent is y over x. You find this r just by using Pythagorean theorem, saying r squared is x squared plus y squared. That's the definition. And you could say r is the square root of x squared plus y squared. And I always want to use the positive value of r. I could say if r squared is 9, r could be 3 or minus 3. I could say that, but I never say that r is a negative number in these definitions. Now I want to show you the Pythagorean identities. So I want you to notice what happens if you take sine squared of theta plus cosine squared of theta. What do you get? Notice now, this is a special notation. When you put the square on the sine, what you're literally doing is taking the sine of theta and squaring it, cosine of theta and squaring it, as they presented in the book. And they don't want you to think you're taking the sine of theta squared. That's why they don't put the square on the theta alone. And writing the square in the parentheses is a lot of writing. So they just shortcut it. Like it's a very old-fashioned notation. Let's just put the square on the sine, which means take the sine theta, then square it. But since sine theta is y over r, and cosine theta is x over r, you can square those two fractions. What happens when you square those two fractions? Y squared over r squared, x squared over r squared. Common denominator, thankfully. So that's x squared plus y squared over r squared. But x squared plus y squared is r squared. I mean, literally the same thing. And so r squared divided by itself is just 1. So what have I shown you? I've shown you the first Pythagorean identity. That sine squared theta plus cosine squared theta is always 1, no matter what theta is. By this definition, that's always equal to 1. Now, how does that relate to this question that was asked up here? Well, that's one Pythagorean identity. There are 3 Pythagorean identities, and I'll show you how to get the other 2. The other two Pythagorean identities are tan squared theta plus 1 is secant squared theta, and 1 plus cotangent squared theta is cosecant squared theta. And these three, all three of these are on our identity list, or our formula sheet. But if you remember one of these, you can make the other two. You can remember all three. And here's how you do it. Let's take sine squared theta plus cosine squared theta equals 1 and divide both sides by cosine squared theta. Remember, if I divide both sides of an equation by the same thing, it keeps it equal. Now, over here, I'll write that as sine squared theta, cosine squared theta. I can think of that as two separate fractions, split over this denominator if I like. But over here, I'm going to start to pull this apart. This is 1 over cosine theta squared. And 1 is equal to 1 squared. So if I'm squaring both the top and the bottom, 1 and 1 squared are the same thing. So I'm allowed to replace 1 with 1 squared. This is 1 over cosine theta squared. But I know that 1 over cosine theta is secant theta. So this is the kind of ability you have to have with those identities. You have to know the reciprocal identities. You have to know the Pythagorean identities. You have to know what it means to square something. So this right here is secant squared theta. Over here, cosine squared theta divided by cosine squared theta, whatever cosine squared theta is 1. But in the first fraction, what I have is sine theta divided by cosine theta squared. Another identity. Sine theta divided by cosine theta is the tangent of theta. So the tangent of theta squared plus 1 is equal to the secant of theta squared. That's that formula. If I divide by cosine squared, if I divide the first Pythagorean identity by cosine squared, I get this identity. You can go and work on the other identity. If you divide sine squared theta plus cosine squared theta equals 1 by sine squared theta, you will get this identity. So these three Pythagorean identities, they belong together. They're siblings, they're brothers, they're sisters. And you can remember them all together. Which ones do you use most frequently? Well, this is the one used number 1 most frequently. But tan squared theta equals secant squared theta comes up a bit. And I could show you in this problem right here. So let's tear that sheet off, excuse me. Look at this problem in the book, 1.5, number 65. And I picked this problem because someone asked me one of the XYZ homeworks that was like it. And it basically says, look at this expression, x squared plus 9, and substitute x equals 3 tan theta. And in the book, it says, assume that theta is between 0 degrees and 90 degrees. And here's the important part. In the XYZ homework, they did not assume that. And so you have a very similar problem with a slightly different answer. First, let's work out this problem. Okay, if I'm going to put 3 tan theta in place of x squared, I'll just write a bigger square root sign. And then I will square two things multiplied together. I have to square the 3 and square the tan theta. 3 squared is 9. Tan theta squared is just tan squared theta. That's how you write tan theta squared, plus 9. And what you have here is two sections, two expressions. They both have a 9. I can factor out the 9 and be left with tan squared theta plus 1, square rooted. But taking the square root of two things multiplied together, I can separate that, take the square root of 9 and the square root of this. I know the square root of 9, but what's the square root of tan squared theta plus 1? Well, I'm going to use my identity. Tan squared theta plus 1 is secant squared theta. So 9 is a perfect square, but this is also a perfect square. Square root of 9 is 3. And now comes the difference between the book and the XYZ homework. They said that theta is some angle between 0 and 90 degrees. I'm not particular which angle, just some angle here in the first quadrant. Now, ordinarily, when you take the square root of something squared, you have to say absolute value of that expression, because that number could be positive or negative before you square it. But the square root has very particular rules on it. The square root can never spit out a negative number. So the square root of 9 is 3, not minus 3. And if I just square minus 3, I don't just say square and square root cancel and the answer is minus 3. No. I say the square of minus 3 is 9, the square root of 9 is 3. Or I could say it like this: the square of the square root of minus 3 is the absolute value of minus 3, which is 3. Now, same thing here. If secant is negative, I cannot say 3 secant theta. I will have to say 3 times the absolute value of secant theta. And I write that right here. Secant theta could be positive or negative. But this is where we're going to use this expression right here. They said theta was between 0 and 90. And secant theta, remember, comes from the cosine of theta. It's the reciprocal of the cosine theta. So in this first quadrant, cosine's a positive number. Again, this is on your formula sheet. If cosine's a positive number, 1 divided by cosine's a positive number, secant's a positive number. So ordinarily, secant could be positive or negative. But here, secant is positive number, and the absolute value of that will be itself. So this is because theta is between 0 degrees and 90 degrees. If I hadn't been told that theta was between 0 and 90, I would have had to leave the answer right here. But I can do this one extra simplifying because I know that the secant theta is positive. I wanted to show you that problem, and I thought that problem was interesting because it was slightly different written in the book and in the homework system. So you got to pay attention to that. Oops, sorry, I got to let someone else in the room. Okay, so you can find problems in the 1.5 homework as you're finishing up for this week that look like this. But if they don't tell you something about the secant theta, if they don't tell you whether secant theta is positive or negative, remember you have to write the answer. with the absolute value bars. Now, I tested this in the system because someone asked me this question, and I was allowed to write 3 times secant theta with parentheses around theta and with the absolute value bar. On a computer keyboard, you might find that in the upper right-hand corner or near the upper right-hand corner. I was also allowed to write according to the instructions. The system gives you instructions for how to write things, and they use the abbreviation ABS for absolute value. So I also wrote the answer like this, and the system accepted it. So you could write either one of those 2 ways. Okay, good. No problem. Now, I know this depends on some other previous knowledge. So if you have questions about this, like, whoa, what's the absolute value? Or why is the square root of u squared equal to u? I mean, we can pop that in a separate video or a separate problem. But this is something you would do in your algebra class before you did this. If it's the first time you see it, then you just got to get used to it quickly, and this is the reason why. Okay. So I wanted to do that example. I wanted to tell you what the Pythagorean identities are. Now let's talk to you about right triangle trigonometry. We define sine, cosine, tangent, and then the reciprocal partners, cosecant, secant, and cotangent. It's really important that you get these straight. Who's the partner of who? Secant is the reciprocal partner of cosine, and cosecant is the reciprocal partner of sine. We define these just by this picture. Draw the angle, find a point, measure the distance, crank the 6 numbers. But there's another way we could define it, because when I talk about X, Y, and R, when I talk about the Pythagorean identity, the first thing that comes to my mind is a right triangle. So let's just say I have a generic right triangle that's sitting on the paper. And let's call this horizontal leg X long, Y long for the vertical leg. Here's the right angle. And let's use hypotenuse is R. Now, normally when I wrote the Pythagorean theorem, or when you write it, you might have said ABC. A squared plus B squared is C squared. But the names of the letters don't change the truth of the relationship. So you could say ABC, you could say XYR, you can use any letters you like, as long as you put them in the right order in the Pythagorean theorem. So Pythagorean theorem says if these 2 perpendicular sides are called the legs, and this is called the hypotenuse. So as you square the legs and add them together, you will get the square of the hypotenuse. Not the hypotenuse, but the square of the hypotenuse. And you also know that once I set this right angle, 90 degrees, all 3 angles have to add up to 180. So if I named one of these angles, you would automatically know the next one. For example, if I said that angle was 10, I didn't draw it looking like 10. Well, if this is 10, this has got to be 80, because these 2 angles have to add up to 90. If this is 20, this better be 70. If this is 45, well, you know this must be 45. So this angle up here, it's a little bit tight, but I'll squeeze it in. will be 90 degrees minus theta. If this is 13, then this is going to be 77. But the cool thing about a right triangle is that you could also define the 6 trigonometric functions exactly the same way. You can define it in terms of an angle and standard position, or you could define Pythagorean theorem, right triangle trigonometry, by using the same x, y, and r. The same formulas written the same way. Y over r is the sine of theta. If someone gives you a picture like this and asks you, what's the sine of theta? You go for the opposite side divided by the hypotenuse. And the reciprocal is r over y. Now, I used a different word there, opposite side, because I was thinking of theta having 3 sides of the triangle. Opposite theta was the y. This side that touches theta is called adjacent to theta. And the hypotenuse is always called the hypotenuse. So some people call the sine of theta, instead of y over r, they call it the opposite side over the hypotenuse. I always misspell hypotenuse. And I better check that as an E or an O. I think it's an E. Okay, don't mind how I spell it. In fact, since most people are afraid of spelling it, they just say like that, opposite over hypotenuse. Cosine can be written as the adjacent side over the hypotenuse. Well, now I got to spell hypotenuse again. Ah, there's an O in there. That was my problem. Adjacent over hypotenuse. Tangent of theta could be written as the opposite side over the adjacent side. Y over x is opposite over adjacent. Sometimes people like remembering it like this because it's more physical. It's easier to look at a concrete triangle. The way we did it originally is still correct also. But you can define all 6 trig functions with opposite, adjacent, and hypotenuse. So get used to thinking of it both ways. Secant theta is r over x, which is hypotenuse over adjacent. And cotangent theta is x over y, which is adjacent over opposite. You can use either language. And right now, I am checking my handout. I can't remember. I think I wrote that also on the handout. So we're going to double check. So when people think like this, okay, I did not write opposite, adjacent, hypotenuse on the handout, but you can add that in when I'm talking about the handout. I'm talking about these formulas. When people describe sine and cosine and tangent and cosecant and secant, cotangent like this, they call it right triangle trigonometry. And remember, the first day we did this class, I mentioned this to you. The word trigonometry means 3-angle measurements. So a lot of people thought about trigonometry this way before they thought about drawing the angle in the standard position like this. There's other ways we're going to think about it too. But sometimes if people say, oh, this is a little bit crazy, I got to find the X and Y and R, and it's hard to see that angle because it could be going around many times. If this doesn't seem like a comfortable way to look at it to you, then look at trigonometry in terms of right angles. And they are both exactly the same. Now there's an issue if I want to do this problem over here, is that I can make you see this problem by drawing a triangle on this problem. And this height of this triangle will be y. And this distance, this number right here would be minus x. The length would be x units long, but in that quadrant, x is negative. So every angle has a triangle attached to it. But when the angle is more than 90 degrees, and this angle is on the left-hand side, and this x becomes negative. If the angle is more than 180 degrees, then the y becomes negative because I'm going downwards on the y-axis. And at the beginning, I don't want to think about that just yet. But I want you to remember this because we're going to say it in a couple days. Every angle in standard position automatically has a right triangle attached to it. And people call that right triangle that's attached to it the reference angle. We're going to come back to this in a day or two because it's going to be the way we connect this description of the trigonometry with this description of the trigonometry. But always remember, trigonometry at its heart is about triangle. 3-angle measurement. That's what the word trigonometry means. So a lot of people start trigonometry with this triangle instead of that other angle. Now I'm going to pick, we're doing right now, we're talking about section 1.5. I'm sorry, section 2.1. So let's take an example out of section 2.1 just to help you out with that. And I'm going to look at, just to warm up, problem number 8. And I'm talking about in your book. So this is a very basic example of how to do this. Here's A. Here's right triangle. I didn't draw that line very straight. If you ever not draw a line straight, the way you fix it is making it thicker. It's kind of like a drawing secret. Of course, I could get out of hand. And I could start screwing up the other lines. Problem number 8, he says, here's A, here's C, and that's a right angle, and here's B. So this is a right triangle. And it says this side is 3, and this side is 4. Can you find out what this side is? And then can you name sine, cosine, and tangent of this angle A? Yeah, so get used to that. Sometimes people put the angle name inside the angle, sine of theta. They also could just name it by the point of the angle. When someone says sine of A, that also says sine of the angle at A. So get used to someone asking you for the sine of A, the cosine of A, or the tangent of A. And this A is just, you call it a point, but it's the angle at that point. If this is B up here, get used to people asking you for the cosine of B, the sine of B, or the tangent of B. We'll do both. So let's check this out. In order to know any of these, I need to know all three sides. So I got to find out what that y is. So Pythagorean theorem time. And you'll do the Pythagorean theorem until you can do it in your sleep. Radius is 4, hypotenuse equals the horizontal side is 3. And I need to know what that side is. So we got 16 is equal to 9 plus y squared. And then subtracting 9, y squared is 7. Now I know in an algebra class, that means y could be plus or minus the square root of 7. But I'm talking about a physical triangle. I'm talking about something I can measure with a ruler. That is not going to be -3 inches or -6 inches. When I'm talking about a physical length, I always pick the positive number. So y is square root of 7. Now I can name sine, cosine, and tangent of A. But I can also name sine, cosine, tangent of B. And watch the cool thing that happens. Let's do A. Sine, opposite over hypotenuse, root 7 over 4. Cosine, adjacent over hypotenuse, 3 over 4. Now I'm using opposite, adjacent, hypotenuse instead of x, y, and r. What's the tangent of A? Opposite over adjacent, root 7 over 3. Maybe if you've ever done this before, that's the way you thought about trigonometric functions, opposite, adjacent, hypotenuse. Notice though, if someone asks you for sine B, it's different because sine B, remember sine still means opposite over adjacent. I'm sorry, opposite over hypotenuse. But for B, the opposite side is a 3. So if someone wants the sine of B, they have to say opposite is 3, hypotenuse is 4, 3/4. If someone wants the cosine of B, they have to say adjacent over hypotenuse, which is root 7 over 4. And if people want to see the tangent of B, then they have to say 3 over root 7, opposite over adjacent for B. There's the angle B. So now is my first chance to tell you what a cofunction is. Oh, excuse me. Let's let people in the room. Sometimes if you see someone waiting in the room, you don't see them waiting, but if your friend is texting you, say, oh, tell Dave to let me in. Maybe that's also a way you get a hold of me in the chat window because I got to keep my eye on that participant window. Okay, you're talking about the famous SOHCAHTOA, remembering sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Some people remember sine, cosine, tangent like that. However you want to assign meaning to it. But it just rolls off the tongue, SOHCAHTOA. It just kind of is poetic sounding. Now, what I want you to see is what a cofunction is. Do you see that the sine of A, look at this, the sine of A is the same as the cosine of B. Notice that the cosine of A is the same as the sine of B. And for that reason, cosine, what we call cosine theta, Cosine is an abbreviation for complementary sine. The cosine is the sine of the complementary angle. What's the cosine of A? 3/4. What's the sine of the angle complementary to A? 3/4. This angle complementary to A is B. Remember, complementary means adds up to 90 degrees. So cosine is a shorthand for complementary sine, or sine of the complementary angle. That's too much to say. So people shortened it to cosine. Look at that. The cosine of A, 3/4, is the sine of the complementary angle B. The cosine of B, √7/4, the cosine of B is √7/4, and that's the sine of the complementary angle A, √7/4. Even cotangent. Now, what's the cotangent of A, and what's the tangent of A, or the tangent of B? Now, what's tangent of B? 3/√7. What's the cotangent of A? Adjacent over opposite, 3/√7. So the tangent of B and the cotangent of A are equal. The cotangent of A just means 3/√7. That is the tangent of the complementary angle. So that's why people use cosine, cosecant, cotangent. We could talk more about that later. This is kind of history, and you don't have to remember or memorize this history. But you can know that there's a reason why people invented that abbreviation, cosine, cotangent, cosecant. Okay, good. So if you look at problems, this is section 2.1. I'll throw it under the camera. When someone says tangent of 90 minus x, the complement of 90 minus x is x. So the tangent of 90 minus x is the cotangent of x. The sine of x is the cosine of 90 minus x. Secant and cosecant are complementary functions. So the secant of 73 is always the cosecant of 17. The tangent of 8 would be the cotangent of 92. And the sine, 82. 90 minus 8 is 82. Sine of 10 degrees is the cosine of 80 degrees. So that's what they call the cofunction identities, or the cofunction theorem. Now, I'd show you this on our formula sheet just to make sure you know that everything you need is on that sheet. That's what we called here the cofunction identities. If you want to know the sine of 20 degrees, you could do the cosine of 70 degrees. If you want to know the sine of 89 degrees, you could take the cosine of 1 degree. Now I'm going to pull out my calculator because that's the next place we're going to go. I just want to show you that even if you don't know the cosine of 89 degrees, your calculator does. Here's a standard TI-84 calculator. Make sure under the mode button, you're using degrees. If you check under there and you're using radians, which we will soon, but you just slide over degrees and hit enter. Now you're using degrees. and quit. So the sine of 10 degrees is this, and the cosine of 80 degrees is exactly the same. Any goofy number you want to name. How about the sine of 15.297? You know, some crazy angle. Well, I'm going to regret doing this because now I got to do 90 minus 15.297. You know what? I could just tell the calculator to do 90 minus 15.297. That feels like cheating, but notice it's the same number. You wouldn't have any confidence in me if I couldn't subtract that. So let's do it by the book. That would be 74.703. And you see it's the same number. So those are really, really powerful identities. They kind of save you time. The co-function identities. Sine of theta is the cosine of 90 minus theta. But you could also say cosine of theta is the sine of 90 minus theta. You could say it either way. Same thing with secant of theta. What is the cofunction partner? It must be the cosecant. Secant of theta is cosecant 90 minus theta. And you could say it backwards. Cosecant theta is secant of 90 minus theta. Last two partners. Tangent of theta is always equal to the cotangent of 90 minus theta. And the cotangent of theta is always equal to the tangent of 90 minus theta. That points out something else interesting on your calculator. And it depends on the calculator you're using, but this calculator, you notice, has sine, cosine, and tangent buttons. Even in the little script blue and green letters above, it does not have secant, cosecant, cotangent. So, for example, if you wanted to work out cotangent on this calculator, they expect that you know the cotangent of theta is 1 over the tangent of theta. They figure you know that already. Or look at this. The cotangent of theta is the tangent of 90 minus theta. If I'm telling the truth, these two things have to be equal. 1 over tan theta is tan 90 minus theta. Let's try it. Suppose you wanted to know the cotangent of 17 degrees. According to what I just said, you could do the reciprocal of tan 17 degrees, or you could do tangent of what's the complementary angle to 17. 90 minus 17 is 73. So if I pop this in the calculator, I've got to get the same answer either way. Let's try it. And remember, I have no cotangent button, so I'm just going to use the tangent button. Let's do 1 divided by tangent of 17, some crazy number. And then let's do the tangent of 73. is exactly the same number. So put this away in your mind. If someone asks you for the cotangent of 17 and you don't have a cotangent button, it's no problem. You do 1 over tangent or tangent of the complementary angle. Me, frankly, I usually do 1 over tangent. And you could do it this way too. Tangent of 17 degrees. And on your calculator, you have a little reciprocal button right here. It's next to sine, cosine, tangent because you need the reciprocal next to sine, cosine, tangent. So if you hit the reciprocal button there, that negative exponent from your algebra days means reciprocal, 1 over tan 17. Do you see you get the same answer? So you could do cotangent of 17 on your calculator in those different ways. Okay, next. So these cofunction identities are useful. Let me say this about them too. You see right here, this was called a reciprocal identity. Keep them straight. This is called a cofunction identity. So in some way, you need to know them both, the cofunction identities and the reciprocal identities that say cotangent theta is 1 over tan theta. So that's why they're both on your formula sheet. They're both equally valuable. Okay, let's try another sheet of paper. Zoom, zoom, zoom. I'm trying to keep track of everything here. Got it. Okay. Give me a second, because try to number these as I go along so I can scan them faster for you after class. Someone asked this question during the office hours today. You record the office hours. Remember, no, I do not record the office hours because I just want you to come and ask questions, whatever you like. Just record these sessions. I do copy the sheets of the questions people ask me at the office hours. Okay. Notice I just jumped straight into what the tangent of 17 degrees is. And you probably said to yourself a second ago, wait, what angle is 17 degrees? That's not one of my famous angles. And this gets into section 2.2. Remember, you have 3 famous triangles, 45, 45, 90. $30, 60, 90. I'm not trying to draw them exactly. I'm just trying to draw them decently. And last one, 15, 75, 90. You know the sides for each of these triangles. Remember, if this is 1 and 1, this side is root 2. You multiply by root 2 to go from leg to hypotenuse on a 45, 45, 90. If this is 1, if short side is 1 on a 30, 60, 90, then the hypotenuse is 2 and the long side is root 3 times the short side. What about 15, 75, 90? That was a goofy one. Put the hypotenuse equal to 4, and then you can write root 6 minus root 2 for the short leg, and root 6 plus root 2 for the long leg. And now you can answer questions like, what's the cosine of 60 degrees? Now you say cosine is adjacent over hypotenuse. So cosine of 60 degrees is 1 over 2. What's the tangent of 75 degrees? Well, you go to 75 degrees in your angle, and you say tangent is opposite over adjacent, and 75 degrees, this is the opposite side. And this, root 6 minus root 2, is the adjacent side. So I want you to think about those three famous triangles that I've just given you. They can give you sine, cosine, and tangent of 45 degrees, 30 degrees, 15 degrees, even 60 degrees, 75 degrees. If you stand this one on its short side, you know the sine and the cosine, tangent, you know all 6 trig functions for these famous angles just by knowing these triangles. Oh, by the way, someone that's going to ask, well, what's the sine of 90 degrees? That's not a triangle. Yeah, but remember, we still have a point on that leg. A point on the side is 0, 1, which is 1 unit away from the origin. So I could say the sine of 90 degrees, y over r is 1. But the tangent of 90 degrees, y over x, 1 over 0, is undefined. So remember, I can use the other way to give me these angles too. But think about this. You know sine and cosine for every angle between 0 and 90 by multiples of 15. But then you're going to come across the question I just gave you. What about 17? What about 35? What about 58? So you don't want to know the sine and cosine tangent. You don't want to know the trig functions only for every 15 degrees. You want to know trig functions for every single degree you could name under the sun and fractions. So you may have memorized these sides and you can name the red ones by heart, and you should do that. You should be able to do that, even if it means drawing a picture. But all these other values, the in-between ones, 58, 57, 56, 55, 54, and so on, these are in your calculator. So if I ask for the tangent of 58 degrees, I'm going to get that number. Now, what's the tangent of 60 degrees, by the way? Tangent of 60 degrees, here's 60 degrees. Up here, sorry, up here near the top. Tangent is opposite over adjacent. So tangent of 60 degrees is root 3 over 1. And the tangent of 58 degrees is 1.6003. I'll stop at 4 digits. Since 58 degrees and 60 degrees are so close to each other, their tangents ought to be close to each other. And what would the calculator do if I asked for the tangent of 60? Well, the calculator says tangent of 60 is 1.732, 1.7321 if I round off to 4 decimal places. Slid off the paper there, sorry. So question in your mind is, calculator says this, Dave says this. Is Dave telling the truth? Well, we can ask the calculator too what the square root of 3 is. And it is exactly 1.732 all the way up to the end. So you and I know the tangent of 60 is root 3 by this triangle. And it's not hard to remember this triangle. The calculator just sees 60 degrees as just another angle. So the calculator has all the angles built in between 0 and 90 and more. But let's just talk about 0 to 90 today. We're talking about section 2122. But sure, if I wanted to say, what's the tangent of 100 degrees, that's over here, I could just type in tangent of 100 degrees. And the calculator would return the number, negative 56713. Now remember, I say when you approximate something on a calculator, at least tell people you're approximating. Square root of 3 is not an approximation, but the 1.7321 is an approximation. So I don't mind if you approximate, as long as you tell people you're approximating and follow the directions of the problem. If the problem says exact answer, you say root 3. Okay. Now, one more thing, and then we're going to wrap it up for today. And that is, we can get very, very particular about angles. So you say you got 58 degrees, 57 degrees, 56 degrees. What about 58.917 degrees? Of course, that doesn't bother the calculator at all. Notice how it's really close to 59 degrees tangent. Which is relatively close to 60 degrees tangent. So the values that the functions put out are close to each other when the angles are close to each other, which kind of feels like common sense. But people don't always write 58.917 degrees. They don't always write degrees in decimals. Sometimes they write degrees in degrees, minutes, and seconds. We talked about Pythagorean theorems to open. We talked about right triangle trigonometry. Now I can find with my calculator the trigonometric values for any acute angle on the calculator. But sometimes you might see people say this. What's the cosine of 37 degrees and 21 minutes? You read that. 37 degrees, 21 minutes. So between 37 degrees and 38 degrees, I'm just making a rough sketch, not true angles. People can use decimals, say 37.5 or 37.1. But in the old days, they used to cut this tiny degree up into 60 pieces and say, cut this into 60 tiny pieces. And each one of those is 1 minute. So 1 minute is 1/60th of 1 degree. 1 minute is a degree divided by 60. So if you wanted to know what 37 degrees, 21 minutes is in decimals, all you'd have to do is take 37 plus 21 times 21 minutes times 1 degree equals 60 minutes. In the calculator speak, it would be 37 plus 21 over 60. And so the calculator, I can't squeeze everything on the paper, 37 plus 21 divided by 60 is 37.35 degrees. In decimal degrees, that's 37.35 degrees. I don't mind if you use decimals. I don't mind if you use degrees in minutes. But some days you're going to read some old stuff, maybe still used among surveyors, still used among engineers in some context. And they might say they have to measure this angle very, very precisely, 37 degrees and 21 minutes. Instead of using decimals, old equipment is cut up into degrees and 60th of a degree minutes. And you and I might say 37.35 degrees, but they say 37 degrees, 21 minutes. You can also have 37 degrees, 21 minutes, and 15 seconds. Every degree is cut into 60 pieces. 1 degree is 60 minutes, but you can also take any minute and cut it up into 60 seconds. There's no way I could draw that. I couldn't even draw the minutes. But if someone says 37 degrees and 21 minutes and 15 seconds, it means I divide by 60 and divide by 60 again, or divide by 3,600. If someone says 37 degrees, 21 minutes, and 15 seconds, what they're saying is 37 plus 21 divided by 60 plus 15 divided by 3,600 is 37.3541 in decimals degrees. So you can ask your calculator what the tangent of 37 degrees and 21 minutes is. Just type 37 degrees and 21 minutes. You could literally type it in like that. You don't have to make a decimal if they don't ask you for one. You could just type 37 degrees and 21/60th of a degree, that's 21 minutes. Calculator would say 763. If you typed in tangent of 37.35, sorry, 5. Calculator would say the same because it's the same number. Okay, we got to wrap it up here. I'll say one more thing. Asking calculators for numbers, the calculator goes on forever. Actually, it does go on forever. You know, this number doesn't stop. In fact, the calculator has 3 more digits off the screen in case you want to do some super rounding. But the real number, 37.35 degrees tangent, actually goes on forever and never stops. So in real life, we're not that precise. You rarely build a kitchen cabinet to the 1/1,000,000th of an inch, right? You might build it to the nearest 32nd of an inch or the nearest 16th of an inch. You know, you always got room to make adjustments. So what this says is when someone gives you a number like this, is it responsible to use all the digits like that? And the answer is no. That's why you saw me rounding off at a certain place. It was in the old days that people just got in the habit of rounding trig functions off to 4 decimal places. But we're going to have to talk about this. How many digits is responsible to use? And so that's the subject for next time. And they're part of the things we're going to do next time. And this is called, you may have heard this before, significant digits. Chemistry, physics, science classes, biology, people are always talking to you about figs, significant figures, or significant digits. And sometimes it gets a bad name, like, oh no, not significant digits. Like I said the answer was 3.7, and my chemistry teacher said the answer was 4, and I got it wrong. Isn't 3.7 rounded off to 4? Well, the answer is yes, but how do you round it off? How many digits should you use? If they mark 3.7 wrong, it's because you should have only used one digit instead of 2. I'll tell you how to tell the difference, and we'll cover that next time, finishing up this week. Okay, dig in to these 2 homework assignments that are due on Tuesday. Send me a question if you have a question. I'm going to cut it off here. And then you can watch this recording later. You guys have a good afternoon. If you have a question, just shoot me an email. I'll talk to you guys later.